Some old quantum theories were established to solve the fatal problems of atoms in Rutherford's model. The most successful one was Bohr's model. Bohr made 4 assumptions in his model. First, the positions of electrons change with time. This concept is typical in classical mechanics and is the same as the Rutherford's model. We will see later, quantum mechanics is different from this. Second, the electrons retain certain orbital states between transitions. This is different from Rutherford's model, which allows the electrons to change their states continuously. Meanwhile, the electrons don't lose energy during orbiting, which contracts classical physics. Third, the electrons change their orbital states when they gain or lose energy by absorbing or emitting light. Such processes are also called transitions. This assumption also contradicts the classical physics because energy in classical physics are continuous. Bohr's model adopts some classical concepts but quantized the energy. That is why it's called old quantum theory. Fourth, the angular momenta of an electron are quantized. L equals nh bar. N is a positive integer. We can use classical mechanics and Bohr's assumptions to find the energies of the states. In classical physics, the centripetal force of circular motion is provided by the electric force. Thus, we have a relationship between speed square and radius. We will use this relation twice. The total energy of the system is the sum of its kinetic energy and potential energy. Pay attention that the potential energy is negative. From the relationship between speed square and radius, we find that the kinetic energy is half of the absolute value of the potential energy. Therefore, the total energy is half of the potential energy. Here, the only unknown value is the radius. We use Bohr's 4th assumption together with the definition of angular momentum. Replace speed square by radius using the previous equation, we can find the expression of radius. Insert this radius back to the expression of energy. We finally find the energies of the states. Suppose one electron transits from the state of N2 to the state of N1, the energy change is in such form. This change of energy is converted to the energy of an emitted photon. The wavelength of the photon can be calculated from Einstein's relation. We find that the expression of wavelength is in accordance with the Rydberg equation. Pay attention that Rydberg equation is from experiments, so Bohr's model successfully explains the experimental result. However, Bohr's model couldn't rationalize its assumptions. Now, we can understand the line spectrum of hydrogen using Bohr's model. The horizontal lines are the energies of the states. The transitions are denoted by arrows. The energy changes during the transitions are proportional to the length of the arrows. For example, Lyman series are the transitions whose final states are n equals 1. They have the highest energy, that is, the shortest wavelength. The line corresponding to the lowest energy in a series is the alpha line. For example, the Lyman alpha line is from n equals 2 to n equals 1. Similarly, the beta line is the second lowest energy line in the series. For example, the Balmer beta line is from n equals 4 to n equals 2.